Alright, let's take a look at another function and sketch it. And again, this is the model, this is the process I'm going to follow. Let's sketch the function 2x minus tangent x, and here we have a restriction on negative pi over 2 to pi over 2. And we might note immediately that the tangent function, if we remember from trigonometry, the tangent function is not defined at pi over 2 or negative pi over 2. It approaches either infinity or negative infinity. It's asymptotic to those values. Alright, so we have a strict domain, so I'm not going to write anything else about the domain. There are no other restrictions on it within that interval. The tangent is defined between negative pi over 2 and pi over 2. We can find by inspection, notice that if x equals 0, f of 0, we know that f of 0 is 0. Because 2 times 0 is 0. The tangent of 0 is 0. F of 0 is 0. And so we know we have an intercept at the origin. I'll go ahead and plot that real quick. We have an intercept at the origin. And that's all we know from that. We might notice that the function is odd. 2x is odd, tangent x is odd, so any sum or difference will also be odd. This is an odd function. So we expect symmetry about the origin, right? That rotational symmetry. So we have origin symmetry. What about vertical asymptotes? We know that as x approaches pi over 2 on the left, tangent x approaches infinity. So then 2x minus tangent x would approach then negative infinity. So I'm expecting an asymptote. I'm expecting the function to go to negative infinity as x approaches pi over 2 from the left. By symmetry, as x approaches pi over 2, negative pi over 2 on the right, I would expect 2x minus tangent x to then approach positive infinity using symmetry. Let's use a little bit of calculus now. F prime of x would then be equal to 2 minus secant square x. Alright, so let's find where this is equal to 0. Alright, so setting this equal to 0, this would then mean that secant square x would equal 2, which means then that cosine square x is 1/2, which means then that cosine x is positive or negative square root of 1/2, which is 1 over the square root of 2, which is root 2 over 2. So then on the domain, negative pi over 2 to pi over 2, then x is negative pi over 4 or pi over 4. Alright, so then let's think of our number line. It's negative pi over 2 to pi over 2. And so here's negative pi over 4. Here's pi over 4. And we can easily test this. Let's test, how about 0? The secant of 0 is 1. So then secant square would be 1. 2 minus 1 is positive. And then testing between negative pi over 2 and negative pi over 4, about negative pi over 3. Then the secant of negative pi over 3 is So let's work this one out. Let's do a negative pi over 3 here. So then I would have 2 minus the secant square of negative pi over 3. All right, the secant, the cosine of pi over 3. So cosine of negative pi over 3 is negative 1/2. No, sorry, 1/2. So then the secant of negative pi over 3 is 2. So then this would equal 2 minus 4, which is negative 2, so this is then negative, and the same thing will happen over here. Just use pi over 3 instead of negative pi over 3. So what is this telling us? F is decreasing on negative pi over 2 to negative pi over 4, increasing on negative pi over 4 to pi over 4, and then decreasing again on positive pi over 4 to pi over 2. We also know that we have a relative minimum. At negative pi over 4, and then substituting that in, we would have 2 times negative pi over 4 minus the tangent of negative pi over 4. So that would be negative pi over 2 plus 1. Which is approximately, that's negative pi over 4, and then approximately negative, I figured this out, negative 0.57. And then similarly, we have a relative max at pi over 4, and then f of pi over 4 would be pi over 2 minus 1. And so that's approximately pi over 4, positive 0.57. Again, there's symmetry there, right? Okay, now let's analyze with the second derivative. So my derivative was 2 minus secant square x, so then the second derivative would be then, let's see, negative 2 secant x to the first, and then the derivative of secant x is secant x tangent x. So that's negative 2 secant square x tangent x. Now secant x, this term can never equal 0. The secant is never 0. Tangent x equals 0. This implies then that x equals 0, right? Because the tangent is 0 if x equals 0. So then analyzing with the second derivative, again, here's my number line from negative pi over 4 to pi over 4. I'm sorry, negative pi over 2 to pi over 2. Then the only thing that matters is what happens at 0. Or I should say it can only change at 0. The secant square is always positive. The negative 2 is always negative. So I have a negative times a positive. And I know tangent changes from negative to positive over 0. And so then it's going to go from positive to negative. All right, because negative 2 times a positive times a negative, that would give me positive over the first interval, and then negative over the second interval. So that tells me I'm concave up on negative pi over 2 to 0, concave down on 0 to pi over 2. And I'll have an inflection point at the origin. I cannot find the limits at infinity, the curve is not defined, we're only focusing on the interval from negative pi over 2 to pi over 2, so no limits at infinity. The end behavior is basically what we've already figured out for the asymptotes in a sense. So let's get an idea over the general shape, comparing the derivative with the second derivative over negative pi over 4. I keep saying 4, negative pi over 2 to pi over 2. And we had important numbers at 0, at negative pi over 4, and at positive pi over 4. And let's see, recalling, the function was decreasing, then increasing, then decreasing, and it was concave up, and then concave down. So decreasing and concave up, increasing and concave up, increasing and concave down, decreasing and concave down. Those are the general shapes. Let's fill in the details with some specific points. All right, we know we have the intercept at the origin. We know that at negative pi over 2 and at pi over 2, the curve is asymptotic. So let's put in, let's say, 1, 2, 3, 4, 5. Here's, I'm going to make this mark here. There's negative pi over 2. So 6 marks to negative pi over 2. And here's positive pi over 2. And I know that my curve is asymptotic up and to the left, asymptotic down and to the right. I know that I have a relative minimum at negative pi over 4 and negative 0.57. So I'll make 6 marks on the y-axis, 1, 2, well, let's just make 4 marks. Here's negative 1, and 4 marks on the y-axis, positive 1. So then at negative pi over 4, negative 0.57, so about there, and positive pi over 4, positive 0.57. The curve is asymptotic, decreasing and concave down. Then it's increasing and concave, decreasing and concave up, then increasing and concave up, then increasing and concave down, decreasing and concave down. And so it turns out that there are two other intercepts, but we cannot find them analytically, but that's not too important for the general sketch of the curve. So here's a rough sketch of the function 2x minus tangent x.